Okay, thank you, everybody. Kai, Udert, and I will be co-presenting this, and we'll be trading it back and forth. So you'll be hearing from him and me in alternation. He'll start out with describing what the scope is of this presentation and getting us started. So take it away, Kai.
Good. Thanks a lot, Abe. Can you hear me?
Yes, we can.
Perfect. Thanks a lot. Thanks a lot for giving this opportunity to present some of our technologies, and it's actually a great pleasure to do that together with you, Abe. So what we will do, I will present some of the, or let's say two technologies which we developed here at ERWAC and which are being commercialized or are already commercialized, and Abe will do the same for the technologies from Brightwater Tools. We all talk about basically returning to a circular strategy. That's the basic concept we're working on. So instead of discharging our nutrients to the rivers, trying to get them out in a wastewater treatment before they actually reach the rivers, we try to capture them and actually produce a fertilizer which can be used in agriculture, and then the food can come back to the cities again where the bio-waste is produced. So we all agree on that. And this is actually a picture which is used by ERWAC because actually the circular strategy or circular economy is one of four foci of the research at ERWAC, which is the Swiss Federal Institute for Aquatic Science and Technology. Okay, let's move to the next slide. So when it comes to urine, the major source of nutrients in wastewater, we have different treatment goals, and the guy actually that you see here in the middle, that's Hennig Brandt. Hennig Brandt, he lived about 400 years ago in Hamburg in Germany, and what he wanted to capture from urine, that's gold. Gold production is not really the major goal of urine treatment anymore. It's more about recovering single nutrients. So this could be nitrogen, phosphorus, or potassium as well, or maybe to recover all of the nutrients. And this can be achieved by water removal. And when we talk about the three processes today, all of them actually, one of the, what is actually in common of all three processes, that's water removal to produce actually a product which could be used as a fertilizer with all nutrients which are excreted from urine. There are also other treatment goals. One is stabilization. Stabilization means that you produce a product which doesn't smell anymore. And for this, COD might be removed or ammonia might be removed. But also risk mitigation might be important, like micropollutant removal, pharmaceutical removal, or the removal of pathogens. There have also been projects on energy production, so microbial fuel cells, for example, and nitrogen removal for actually to enhance the treatment in wastewater treatment plants. So urine could also be captured at the households, and the nitrogen is removed, for example, with the Anammox process. Again, the main treatment goal here for the three processes we will present is water removal, but also risk mitigation. With this, actually, I hand over to you, Abe.
Okay. Thank you. So I'll be talking first about what Rich Earth does with a fairly simple treatment strategy, and then after Kai introduces some of the more advanced methods available, I'll talk about what Brightwater is doing using some higher levels of technology. So at Rich Earth currently, we have a urine collection program in the town of Brattleboro in Vermont, and it uses various permanently plumbed fixtures as well as portable fixtures. So we have a number of divided bowl toilets that are out in the community and other fixtures that collect urine into a pipe and then down into a storage tank. And in these houses where there are these permanently plumbed fixtures, then we show up with the pump truck and evacuate that using vacuum suction. So there's no treatment in the house. It's just held and then pumped out. There's Arthur Davis, who's here today, pumping it out. And then we bring that urine to our treatment facility on a truck. So we're carting all of this unprocessed urine on a truck to where we can then process it. And the processing we use at the Institute is a simple single-step process of pasteurization. So we bring it up to a high temperature and kill any pathogens that are in there, then cool it back down in a heat exchanger. And that meets the requirement that the state of Vermont has for for pathogen removal. I want to stress here that even this treatment is not actually required if you're doing this on the home scale. World Health Organization has some guidelines on how to handle and manage urine fertilizer. You don't need a pasteurizer, but in our case, for a community scale project, we do use a pasteurizer to ensure public safety and comply with regulations. Then after that pasteurization step, we take the urine and we apply it on farmland. And so it goes onto the soil, absorbs into the soil, and provides fertilizer to the growing plants. So there's no stabilization step here. There's no volume reduction step. It's just pathogen removal. And this is practical in a small geographic area because we're not moving the urine very far from these homes, and we're not taking it very far to get to farm fields once we've processed it. And so that's all well and good in this situation. We've also tried other crops as well, like growing corn. You can see that this farmer, John Janison, has a urine tank on the back of his tractor, and it gets applied as he cultivates his corn underneath. But at this point, we're getting into a situation where it was easy to get the urine to his field, but it becomes labor intensive to go back and forth to refill that small tank with urine every time he runs out. It would become a lot more labor efficient and also some energy efficiency in the tractor operations if we could concentrate that fertilizer into a smaller volume, so it could be stored, transported, and handled in a smaller volume. So the nutrient density goes up if you concentrate it. Conventional fertilizers you'd buy in solid form often have 30 times or more higher nutrient concentration than unconcentrated urine. And by reducing that volume, you get efficiencies and economic benefits at all stages of the process. Of course, with the trade-off of higher investment for treatment technology, and there's some energy and cost in the treatment itself. So with that, I'll turn it back to you, Kai, to talk about the various types of treatment processes.
Yeah, thanks a lot, Dave. So we can differentiate between biological, physical, and chemical processes, and there's also this niche of electrochemical processes, which mainly aims at recovering energy also from urine. But I think most of the processes which are being explored are the biological, chemical, and physical ones. Biological, we need some microorganisms actually to degrade the organics, also convert ammonia into ammonium nitrate. Algae growth as well. Here we already go to actually producing something which can be used later, for example, as a fertilizer. Those could be algae. And then we have a whole range of physical and chemical processes. And most of those processes have been investigated in the lab, so at universities, research institutes, and only a few of them have actually been implemented in practice. And so maybe we can go on to the next slide. And this is actually the Brightwater treatment train.
Yeah. So I'll present what the Brightwater treatment train is, and then Kai will talk about what's happening with Vuna and EVAG. So the Brightwater train has several components. There's the collection fixtures. It can be any kind of fixture. Then the urine flows to a freeze concentrator, and that uses a freeze thaw process, which is one of the ones that was on Kai's slide previously. Anytime you partially freeze a solution of water and things dissolved in the water, you get pure water ice, and then all of the things dissolved in the water stay in the unfrozen portion. So if you partially freeze it, you get pure ice plus all the nutrients in our case and salts in a smaller volume. So if you then drain out that unfrozen liquid, you can get a concentrated fertilizer and this water ice, which can then be melted and reused or treated and disposed of. So we get a concentrated fertilizer out of the freeze concentrator. That then goes through the same pasteurizer, and then optionally can go through a carbon filter to remove micropollutants, which there's some considerable debate about whether that's actually necessary for urine-derived fertilizer, but it's something that is part of the Brightwater treatment train, optionally if it's desired. And the end result is a concentrated, sanitized fertilizer. It's sanitized and concentrated, purified potentially, but it's not been stabilized or deodorized. That can happen as an additional step, but it's not a necessary step actually into making an agricultural grade fertilizer. So this is a very simple, purely physical process. I'll just skip over this slide quickly, but I want you to see this nice rainbow of colors. There's the feedstock on the right, concentrated urine on the left, and then on the right, the clear urine or the clear liquid is the purified water that can be removed. So this represents the product of a run of freeze concentration. The image below is the prototype freeze concentrator. The thing I want you to see is it has two chambers. This is like our lab scale one from a few years ago. Two chambers. One chamber is frozen while the other chamber is melted. And the real innovation that Brightwater is doing here, well, a few of them, but one of them is it uses the ice block as a sink to pull the heat out of the freezing chamber with a heat pump and dump it into the ice block, which lets it operate very efficiently because the freezing and the thawing temperatures are very close together. So there's very little temperature difference. So this is the current rendering of our system, and actually that is what it looks like. You'll see it if you come to the open house tomorrow. We have a system just like this that's built in our facility you can look at, and it runs up about 100 liters per day. That's expandable, and it is, like I said, purely physical. There's no biology involved, so it's quite robust, and it makes a fertilizer that's high in ammonia and ammonium. And we have 2 beta units slated for France and for Switzerland, which you can also see in production at our facility. So that's for the Brightwater train, and now I'll pass it back to you, Kai, for the Swiss systems.
Yeah, thanks a lot, Abe. So here are 2 examples. On the left side, the Vuna technology. Rosanne already mentioned the Vuna technology has been developed at EAVAC and is now commercialized by the company Vuna Nexus. It's a biological physical process. So the core actually is the conversion of the free ammonia into ammonium nitrate, with the goal actually to prevent any ammonia loss. At the same time, 90% of the organics are degraded. This is a treatment application which is pretty similar to the Brightwater tools application. So it's for 100 liter per day or more, so rather large installations. The big advantage is actually there's hardly any nutrient loss, except maybe for the phosphorus that precipitates during storage. So if you collect urine, there will be urea hydrolysis. We all know about that, and about 30 to 50% of the phosphorus can precipitate. But depending on the way how you treat the stored urine, for example, if you store it before you transport it into the nitrification reactor, then you can still recover this phosphorus. On the right side, it's the nutrient harvester. So the application for this system is actually more on-site, so on-site at the extremum. So that means directly at the toilet. So there will be no piping involved at all. So the urine will be treated directly after, for example, this urinal here. It's a purely chemical physical process. And the goal was here to be really independent of any biological process. Only about 10 liters per day can be treated, but that should be enough for this single installation. And the product will be a solid urea fertilizer. And to produce a solid urea fertilizer, it's really necessary to stabilize the urine directly after the collection. So here actually calcium hydroxide is added, and the stabilization happens at a high pH value. We're still working on the development of this process, and the startup will actually be funded in the coming months to commercialize this system. Okay, we can move on to the next slide. Very quickly, the 2 processes. First, the Vuna. So we collect the urine, urea is hydrolyzed, and we have the biological treatment, so the transformation. Then we also have activated carbon. And then we have the concentration step. And this concentration step is a distiller. And the advantage of the distiller is that we actually also pasteurize the solution as well. So we kill the pathogens here, and then we concentrate solution and produce Urine, which is a fertilizer which is actually on the market and has a license in France, Austria, Liechtenstein, and Switzerland. And then the next slide. This process has been installed, or this urine collection system has been installed in 5 buildings on the campus of EAVAC and EMPA. So that's the sister institute. So we have it here in 5 buildings. And that's the next slide. It's also installed here. That's the headquarters of the European Space Agency. The reason for that is that the nitrification actually of urine is also a core process of the Melissa project. The Melissa project is one of the European Space Agency's project with the goal to use biological processes for life support systems for space missions. Okay, next slide. This is now the nutrient harvester process, and here we use alkaline urine treatment. This was actually developed for applications in low-income countries, and we chose actually this chemical physical process with the assumption that it will be more robust, so it doesn't depend on biology. And it basically has two steps. The first one is the stabilization. So in one reactor, actually a base, in this case calcium hydroxide, is added. pH rises to 12.5. At this high pH value, actually microorganisms are killed. And so we have the pasteurization, or at least removal or killing of the microorganisms. And we also prevent urea degradation. And in addition, fermentation as well, because fermentation is actually the process which is responsible for the bad smell of urine. After that, the urine goes into the evaporation reactor, and we use high areas, surface areas, to spread the urine, and then actually ambient air is blown over this surface area, over this trace, to remove the water. And what's important, we use low temperature, so ambient temperature, because if we use high temperature, 70, 80 degrees Celsius, the urea would be degraded chemically, and we would lose the ammonia as well. So we can go to the next slide. Now, this process was developed for low-income countries. Now it's being developed also with those two gentlemen, that's David Hassler and Michael Riechmann, in a project here at ERWAC to really scale it down and bring it into a form that it could be installed directly in the bathroom. So it would be possible to actually introduce that into a bathroom, and then from time to time, you would have to replace the calcium hydroxide, and you could actually recover the solids at the bottom, or they might still be slightly moist, and this could be later produced into a granulated fertilizer, for example. Okay, so next slide. This here, that's a comparison of the fertilizer products. So we have basically 4 products. So the Brightwater product and Urine Pro. What is Urine Pro? This would be a more concentrated solution of urine. The big difference is 3 times higher concentrations, but also higher energy demand. And then the Granurine. Granurine, this is something very similar to what we produce in this nutrient harvester, but it's produced by Sanitation 360. Sanitation 360, a company, Swedish company, which applies 2 processes, alkaline and acid stabilization. And alkaline stabilization is really similar to the nutrient harvester. Okay, what do we see? We have pathogen inactivation in all processes. Different degree of nutrient recovery and concentration, but also high difference in the energy demand. So Brightwater tools process has a very low energy demand compared to the other processes. Something which is missing here might be the possible loss of ammonia or organic compounds, which is not in the list. But I think there will be different applications for the different products. So I think there is definitely a chance for all of those processes to be implemented.